Our universe may not be all reality. All the space that we see, measure, and think of as infinite can be just one layer within a much more complex structure. Huge galaxies, black holes, dark matter, billions of light years of emptiness, all this can be located on a kind of cosmic surface, hidden inside space with a large number of dimensions. There is an even stranger possibility. A space that seems to be the fundamental foundation of the world may not be primary at all. It can arise from information encoded at the far edge of reality. Then depth, distance, and even gravity will turn out to be not independent properties of nature, but manifestations of a deeper level, which is not yet directly visible. But where does science end and a beautiful mathematical hypothesis begin? We are used to considering the universe as the last limit of everything that exists. It is as if there can be nothing behind it, because the very word universe means all space, all matter, all energy, and all time. However, modern theoretical physics allows for a different picture. The space in which stars and galaxies move can only be part of an architecture, much of which is hidden in extra dimensions. These measurements are not necessarily somewhere far away. They may be present at every point in space, but they're so small or so unusual that ordinary matter is unable to move in their direction. We see only three spatial dimensions: length, width, and height, but mathematical models allow for the existence of other directions that are inaccessible to our senses and modern devices. At the same time, it is important to immediately draw a clear line. The expansion of the universe, the CMB radiation, the motion of galaxies, and the properties of black holes are confirmed by observations. Additional dimensions, branes, and the holographic nature of space are still theoretical ideas. They may be mathematically consistent and explain some of the mysteries of physics, but there is no direct evidence for their existence yet. To understand why such hypotheses arose in the first place, we first need to see the true scale of the part of the cosmos that is available to us. The observable universe has a diameter of about 93 billion light years. At first glance, this seems strange because its age is approximately 13.8 billion years. Light could not travel a distance greater than the age of the universe in light years. But while the ancient radiation flew towards us, space itself continued to expand. The regions that emitted this light billions of years ago are much farther away today than when it was born. Within the observed region are hundreds of billions of galaxies. According to some estimates, their number could be as high as 2 trillion if we take into account extremely weak and distant systems that cannot yet be seen directly. The exact number is unknown. Many of these galaxies are so faint that their light is lost in the depths of space, and some existed only in the early stages of the universe's development and have long since changed their shape or disappeared as a result of mergers. Galaxies are not randomly distributed in space. They form gigantic filaments, knots, and walls separated by huge voids. This structure is called the cosmic web. In its dense nodes are clusters of galaxies, and long filaments stretch through hundreds of millions of light years. Between them lie areas where there are much fewer galaxies. The main role in the formation of this web was probably played by dark matter. It does not emit light or absorb it in the usual way, but it does create gravity. It was around its invisible clusters that the matter from which galaxies, stars, and planetary systems later arose. And yet, this incredible structure occupies only an observable part of the cosmos. 93 billion light-years is not the proven size of the entire universe. This is only the limit of the area from which the light has reached us. Beyond the cosmological horizon, space probably continues further, but it is impossible to see it because the signal from there has not yet reached the Earth and may never reach us due to accelerating expansion. don't know how big the whole universe is. It can be much larger than the observed area. It can be endless. It can also have complex geometry and close in on itself so that movement in one direction will someday return the object to its starting point. Modern observations show that space on available scales is very close to flat, but this does not prove its infinity. This is where the first troubling question arises. If everything we see is only a small available region, then could the universe itself be part of something even bigger? Can our entire cosmos, with all its galaxies, exist as a single layer within a multidimensional structure, the size and structure of which cannot be described in familiar terms? For the answer, the physicist turns to the idea of additional dimensions. And this idea begins with a simple mental experience. Let's say there's a world that has only 2 dimensions. Its inhabitants are able to move forward, backward, left, and right, but there is no upward direction for them. They will never be able to leave their plane and will not be able to see an object above it. For them, all reality will be limited to the surface. If a 3-dimensional sphere passes through such a world, its inhabitants will not see the entire sphere. First, a dot will suddenly appear in their space. Then, it will turn into a small circle. The circle will begin to grow, reach its maximum size, after which it will begin to shrink and disappear. For the creatures of the 2-dimensional world, it will be a mysterious object that emerges out of nowhere and dissolves without a trace.
But in 3-dimensional space, nothing supernatural happened. The sphere simply crossed the plane. 2-dimensional observers did not see the entire object, but only a sequence of its sections. And now there is a much more difficult opportunity. What if we are in a similar position? What if objects from higher dimensions could cross our space, and we could only see their 3-dimensional sections? Then some phenomena might seem sudden, strange, or disruptive to the usual picture of the world, just because we do not observe the whole process. This analogy does not prove the existence of additional dimensions, but it shows why a limited being can overlook a direction that is not part of the structure of the reality available to him. It is on this principle that some of the most daring models of modern physics are built.
Then each point of the familiar space can contain hidden multidimensional geometry. At large scales, it remains imperceptible, but at extremely small distances, it is able to determine the properties of particles and interactions. The shape of these collapsed dimensions could affect what particles exist, how much mass they have, and how they interact with each other. There is another possibility. The extra dimensions may not be microscopic, but quite large, but ordinary matter remains bound to our 3-dimensional layer. In this case, we are not able to leave it, not because there are no other directions, but because known particles cannot move freely outside of it. This is where the concept of brane appears. This is an abbreviated name for a multidimensional membrane that can exist inside a space of a higher dimension. Such a brane does not necessarily look like a thin surface in the usual sense. It can have 3 spatial dimensions and include the entire cosmos we observe. Then each point of the familiar space can contain hidden multidimensional geometry. At large scales, it remains imperceptible, but at extremely small distances, it is able to determine the properties of particles and interactions. The shape of these collapsed dimensions could affect what particles exist, how much mass they have, and how they interact with each other. There is another possibility. The extra dimensions may not be microscopic, but quite large, but ordinary matter remains bound to our 3-dimensional layer. In this case, we are not able to leave it, not because there are no other directions, but because known particles cannot move freely outside of it. This is where the concept of brane appears. This is an abbreviated name for a multidimensional membrane that can exist inside a space of a higher dimension. Such a brane does not necessarily look like a thin surface in the usual sense. It can have 3 spatial dimensions and include the entire cosmos we observe.
If this hypothesis is correct, then galaxies, stars, planets, and all known matter are inside the same brain. The space around it can contain additional dimensions, which in some models are called a beam. At the same time, most of the known interactions remain locked in our armor. But gravity can behave differently. It is much weaker than other fundamental interactions. The electromagnetic force, for example, is capable of holding atoms and molecules together, whereas gravity becomes noticeable predominantly at enormous masses. One hypothesis explains this weakness by the fact that gravity may partially extend beyond our brain, going into additional dimensions. If some of the gravitational influence does leave the available space, then inside our world it looks weakened. This idea remains a hypothesis, but it shows how additional dimensions could not manifest directly, but through subtle deviations in the behavior of gravity.
To test such assumptions, the law of attraction at very small distances is investigated. If gravity begins to behave differently than conventional physics predicts, this could be an indirect sign of hidden measurements. So far, no reliable deviations have been found. The abusive model allows for an even more radical picture. Our universe may not be the only membrane. Somewhere nearby, but not in the usual direction, there may be other branes. They are able to be very close to us in a space of a higher dimension, remaining completely invisible. Other physical conditions could operate on these branes. There could be different values of fundamental constants, different sets of particles, or a completely different structure of matter. But there is no direct data on the existence of such worlds. This is a consequence of some mathematical models, not a confirmed picture of reality. Sometimes the question arises, can another brane pass through ours? In some scenarios, the brane interaction is seen as an enormous scale. Their convergence or collision could release a colossal amount of energy and trigger a hot phase of the universe's development. Epiotic cosmological models are based on this. According to one version, before the expansion began, the universe could have gone through a long phase of slow contraction. Then the brane interaction occurred, after which a hot and dense stage began, reminiscent of the early universe of standard cosmology. However, caution must be exercised here. Relic radiation and expansion of space do not prove a collision of branes. These observations are successfully explained by the standard model of the hot early universe without additional measurements. The epiotic scenario remains an alternative theoretical possibility, which does not yet have unambiguous observational confirmation.
The main difficulty of such models is related to the transition from contraction to expansion. It is necessary to explain how the universe could escape a destructive state with infinite density and move on to a new phase. The mathematical description of this point remains one of the most difficult parts of the theory. But even if branes never existed, the idea of a hidden structure of space also arises in another direction of physics, the holographic principle. At first glance, the word holographic gives the impression that our world is an illusion or an artificial image, but the scientific meaning of this idea is much more precise and complex. A conventional hologram stores information about a three-dimensional image on a two-dimensional surface. The depth we see arises from a structure recorded on a flat carrier. In physics, a similar idea appeared when studying black holes.
A black hole has an event horizon, a boundary after crossing which light can no longer return to the outside. Matter and energy are hidden inside this region, but the amount of information associated with a black hole suddenly does not depend on its volume. It is proportional to the area of the event horizon. This is one of the strangest results of theoretical physics. It can usually be expected that the larger the volume of a system, the more information it is capable of containing. But in the case of a black hole, the maximum information capacity is determined by the area of its boundary. So there was an assumption that such a principle could be fundamental. Perhaps information about space and everything inside it can be described at the boundary of a smaller dimension.
A black hole has an event horizon, a boundary after crossing which light can no longer return to the outside. Matter and energy are hidden inside this region, but the amount of information associated with a black hole suddenly does not depend on its volume. It is proportional to the area of the event horizon. This is one of the strangest results of theoretical physics. It can usually be expected that the larger the volume of a system, the more information it is capable of containing. But in the case of a black hole, the maximum information capacity is determined by the area of its boundary. So there was an assumption that such a principle could be fundamental. Perhaps information about space and everything inside it can be described at the boundary of a smaller dimension.
Then the three-dimensional world is not necessarily primary. It can arise from a deeper structure existing on a two-dimensional boundary. This does not mean that everything around is fake. If space arises from information, it still remains a physical reality for all processes within it. The most famous example of this approach was the correspondence between the theory of gravity in a certain type of space and the quantum theory at its boundary. This idea is called ADS-CFT compliance. It shows that two very different theories at first glance can describe the same physical system. Gravity acts inside space, and at its boundary there is a quantum theory without gravity. At the same time, the events in one description have an exact match in the other.
It has become a powerful tool in theoretical physics, but the space for which such a connection is best designed is different from our expanding universe. Therefore, it cannot be said that our entire cosmos has already been proven to be a hologram. To put it another way, some models show that space and gravity can be emergent phenomena. They can emerge from more fundamental quantum connections, just as a complex structure arises from many simple elements. Then the distance between objects can be related not only to geometry, but also to the amount of quantum information that unites different regions. The more closely connected the parts of the system, the closer they can be in the emerging space, and the weakening of these bonds can literally change the geometry.
In such a picture, space ceases to be an empty stage on which events take place. It itself becomes the result of interactions. Without information and quantum connections, familiar geometry may not exist at all. This is one of the deepest ideas of modern physics, but it does not yet give a definitive answer to the question of the nature of our universe. We do not know whether the holographic principle applies to the entire real cosmos as it exists today. And yet, the very possibility changes the view of space. What seems continuous, fundamental, and independent can only be an external manifestation of a deeper level. Galaxies, distances, and even the direction of motion can be the result of a structure that cannot be seen directly.
But if space is able to arise from a deeper information structure, then the universe itself may not be as it appears from the inside. What we perceive as a huge three-dimensional volume can only be one form of describing the processes taking place at a fundamental level. In this case, the question of the boundary of the universe acquires a new meaning. Perhaps space has no edge in the usual sense. Its limit may not be a physical wall, but an area where information about all internal contents is stored. However, so far this is only one of the interpretations of the holographic principle, and it must be applied directly to our cosmos with great caution. Modern cosmology also considers another way that can lead to the existence of many universes. It is not directly related to either the branes or the holographic border. We are talking about eternal inflation. According to the inflationary model, space experienced a period of rapid expansion at an extremely early stage. In a tiny fraction of a second, the size of individual regions could increase enormously. Such a hypothesis helps explain why the observable universe looks so homogeneous and why its geometry is close to flat. But in some versions, inflation may not have ended simultaneously everywhere. In some areas, the rapid expansion stopped, after which hot matter arose there and began a development similar to the history of our cosmos. In other areas, inflationary expansion continued. This could have led to a process that never ends completely. Space continues to swell, and within it, separate areas are born where inflation stops. Each of them can turn into an independent bubble universe.
Our cosmos in such a model would be just one of countless regions within a much larger inflationary space. Beyond the observable horizon, there could be other bubbles, so far away from us that no signal could ever cross the space separating them. Some versions of this hypothesis suggest that different bubble universes may have different physical properties. They can differ in the masses of particles, the strength of the interactions, the structure of the vacuum, and even the number of measurements. This is due to the fact that fundamental fields can pass into different stable states. If this is possible, then our set of physical laws may not be the only one. It may be just one of many options implemented in various areas of the wider reality.
But here, science faces a serious problem. If the other bubble universes are permanently separated from us, they cannot be observed directly. It is impossible to point the telescope beyond the space from which light can reach the Earth. You cannot send a device there or receive a message from there. Therefore, the hypothesis of eternal inflation remains the subject of controversy. It arises from some mathematical models, but it is extremely difficult to test it in its entirety. Possible traces of collisions of bubble universes, which theoretically could be preserved in the CMB, are being investigated. So far, no convincing and generally accepted evidence of such clashes has been found. Obscene cosmology and eternal inflation are sometimes combined in popular stories about the multiverse, but they are different ideas. In the first case, our cosmos is considered as a membrane in a space of a higher dimension. In the second, it is like a region that has arisen within the ongoing inflationary process. Both models assume the existence of a reality that is superior to the observable universe, but none of them have yet been confirmed enough to be considered an established description of the world. How can one look for traces of what is hidden beyond the usual dimensions? One way is related to gravity. If it is able to propagate into additional dimensions, then at very short distances, the law of attraction may differ slightly from the usual one. The more accurate the measurements become, the smaller deviations can be checked. So far, the results are consistent with known physics, and no reliable latent dimension signal has been found. The other way is related to high-energy physics. Particle collisions can result in processes that cannot be explained by just 4 dimensions of space-time. Some of the energy could theoretically go into a hidden dimension, giving the impression that it has disappeared. However, the loss of energy can have other causes, so any such result would require very rigorous verification.
They are also looking for possible hard states of particles that could be manifestations of motion in additional dimensions. So far, not a single unambiguous confirmation has been found. Cosmology offers another source of information: CMB radiation. This is the oldest light that modern space is capable of observing. It's separated from matter about 380,000 years after the expansion began, when the universe became cold and transparent enough. Slight changes in the temperature of the CMB radiation contain traces of the density of the early matter. It was from these primary inhomogeneities that galaxies and clusters later grew. If unknown processes were at work at the very beginning, they could leave weak features in this radiation. Episodic and inflationary models can predict different properties of primary perturbations. Especially important are possible ancient gravitational waves and the degree of deviation of the density distribution from the simple Gaussian form. So far, the available data agree well with the standard cosmological picture, but do not give a definitive answer to all questions. Some model options are already limited to observations, while others are still possible. Science is moving very slowly here because it investigates processes that took place almost 14 billion years ago at energies that are inaccessible to modern experiments. Each new result doesn't necessarily reveal a hidden dimension. More often than not, it only narrows the space of possible explanations.
This is the main difference between a scientific hypothesis and a beautiful story. It is not enough to create a mathematically impressive model. It must make predictions that can be verified and stand up to comparison with real observations. String theory, battle worlds, eternal inflation, and the holographic principle do not yet form a single proven picture. They belong to different areas and solve different problems. Sometimes they intersect mathematically, but that doesn't mean they all describe reality at the same time. Perhaps some of these ideas will turn out to be correct. Perhaps some of them will be replaced by more accurate theories. It is also possible that additional dimensions will never be discovered, and space will turn out to be fundamental exactly as it is described by modern physics.
But even now, these models reveal an important idea. Human perception does not determine the structure of reality. The fact that we see only 3 spatial directions does not yet prove the absence of others. The fact that space appears continuous does not guarantee that it remains so at the deepest level. The observable universe may be just a small region of a much larger cosmos. It can be a brane, an inflationary space bubble, or an emerging geometry associated with quantum information. Or it may turn out to be the only reality, beyond which the question of the existence of something loses its physical meaning at all. So far, none of these options can be called a definitive answer, but each of them makes you look differently at the cosmic web, stretching through billions of light years. Perhaps all its filaments, galaxies, and voids do not form the highest level of structure, but only one fragment of a much more complex canvas.
And if our universe is indeed part of such a hyperstructure, then the familiar notion of outer space may be wrong. There doesn't have to be a void outside our space. There may be a medium of a different dimension in which entire universes are arranged as separate regions of one larger system. But the word "located" here can also be inaccurate. The distance between such worlds cannot be measured in kilometers or light years, because these units refer to the space within our universe. The 2 branes are able to be extremely close in an extra dimension, and yet remain completely inaccessible to each other for ordinary matter and light. This means that another world could theoretically be located not billions of light years away, but as if near every point in our space. However, the direction leading to it would not coincide with any of the directions we know. It would be impossible to turn the telescope in the right direction, or build an apparatus capable of crossing such a boundary. That would require physics to which ordinary matter may not obey.
Gravity remains one of the few possible mediators between such regions. If it is indeed capable of extending beyond the brane, then massive objects in another layer could have little effect on our world. But there is no evidence yet that the observed gravity is caused by matter from a nearby brane. Most of the effects that are sometimes tried to be associated with such ideas have simpler explanations within existing models. For example, dark matter manifests itself through gravity, but that doesn't mean it's in another dimension. Observations of galaxies, clusters, and the cosmic web are consistent with the existence of invisible matter within our space. The hypothesis of matter on the adjacent brane remains much more speculative and is not necessary to explain the known data. However, the possibility itself shows how limited our understanding of the content of reality can be. We are used to looking for unknown objects inside space, but some mysteries may be related not to a new kind of matter, but to the very geometry of the world.
Perhaps space has additional directions that become noticeable only at incredibly high energies. Perhaps these directions are folded into microscopic structures. They may exist on an enormous scale, but access to them is obscured by the fundamental properties of particles. Each of these options leads to different predictions. In one case, new particles must appear. In the other, the behavior of gravity changes. In the third, the early universe must have preserved special traces in relic radiation or gravitational waves. So far, not a single such signal has been recognized as definitive evidence. And this is important because the lack of confirmation does not automatically mean that the idea is false, but it does not give the right to present it as an established fact.
The history of physics knows theories that remained mathematical assumptions for decades before they received observational support. But there were also extremely beautiful models that did not describe nature in the end. Mathematical consistency is a prerequisite for a good theory, but it alone does not prove that nature chose this option. Therefore, the question of multidimensionality remains open.
Perhaps future measurements will reveal a deviation from the known law of gravity. Perhaps new observations of the early universe will reveal a structure that cannot be explained without additional measurements. Or perhaps all the data obtained will continue to confirm four-dimensional spacetime without any hidden directions.
But even the absence of extra dimensions will not make the universe simple. Within the already known space, there are questions to which there are no final answers yet. We don't know the nature of dark matter. We do not understand why the expansion of the universe is accelerating. We do not have a complete theory that combines gravity and quantum physics. It is the attempt to combine these two descriptions that leads to the deepest problems. General relativity treats spacetime as a smooth geometry that is curved by matter and energy. Quantum physics describes the world through probabilities, fields, and discrete interactions. Both theories work extremely accurately in their fields, but in extreme conditions, they begin to conflict.
At the center of the black hole, and in the earliest states of the universe, gravity becomes so strong and the scale so small that a single quantum description of spacetime is required. It is here that habitual geometry can cease to exist as a continuous structure. Some models assume that space is made up of tiny elements, others associated with quantum entanglement. String theory introduces fundamental oscillating objects and additional dimensions. The holographic principle admits that volumetric geometry is encoded at the boundary. Despite the differences, many of these approaches lead to a similar thought. Space may not be the original basis of reality. If this is true, then the concepts of distance and direction arise only at a certain level. At a deeper level, there may be relationships between quantum states that are not similar to conventional geometry. Space appears only when a huge number of such connections are organized into a stable structure.
Perhaps the early universe once did not possess space in the modern sense. It could be in a quantum state from which geometry, time, and separation between objects gradually emerged. Then, the Big Bang would not be an explosion of matter inside a finished void. It would signify the beginning of the expansion of space itself, or even the transition from a more fundamental state to a space-time reality. Standard cosmology does not describe the moment of the absolute beginning. It confidently restores the development of the universe starting from very early hot stages, but when approaching the ultimate energies, its equations cease to be sufficient. Therefore, the question of what happened at the very beginning remains open. Perhaps there was compression before the hot stage. Perhaps there was a clash of brains. Perhaps our region emerged as a bubble within the inflationary space. Perhaps the very concept of before does not apply, because time arose with the universe. None of these options has yet been proven.
Yet each of them points to one common problem. The limit of our knowledge is not only billions of light years away, it is located in the very structure of space and time. We can observe extremely distant galaxies, the light of which began to travel to us shortly after the appearance of the first stars. We can measure the CMB radiation that has preserved information about the young universe. We can detect gravitational waves from collisions of compact objects. But the closer we get to the origin of space, the less direct data remains. The early universe is hidden beyond the transparency of matter, and even earlier epochs are only accessible through indirect traces. Therefore, any theory about the deep structure of the cosmos must be extremely rigorously tested. The bolder the statement, the more accurate the prediction should be.
If an additional dimension exists, it must leave a measurable effect. If space is an emergent structure, this idea should explain the observed properties of gravity. If our cosmos collided with another region, the traces of such an event should be detectable and distinguishable from random data features. So far, the search continues. And perhaps the biggest difficulty is that nature is not obliged to reveal all its levels through the experiments available to us. Some processes can occur at energies that cannot be created. Others are beyond the horizon of the observable universe.
Still others may not leave unique traces that allow you to distinguish one model from another. Then several different theories are able to explain the available observations equally well, but give completely different pictures of reality. In this case, science will not be able to choose between the two until a new type of data appears.
This is not a defeat. This is an honest limit of knowledge. We know that the observable universe is expanding. We know that its age is about 13.8 billion years. We know that galaxies form a cosmic web, and that most of the gravitating matter remains invisible. But we do not know whether the observed region is a small part of infinite space. We don't know if there are additional dimensions. We don't know if there are other branes or bubble universes. We do not know whether space is fundamental or arises from a deeper level. It is this uncertainty that makes the question of the cosmic canvas so strong.
Perhaps all the galaxies that will ever be seen are inside the same layer, hidden among other levels of reality. Perhaps the entire cosmic web is just a structure on the surface of an object whose true form extends in directions that we are unable to perceive. Or perhaps there is no external hyperstructure, and the universe itself is a complete, closed reality. But even so, its internal structure remains deep enough to hide the fundamental nature of space, time, and matter for a long time.
Perhaps the main question is not even whether something exists outside our universe, but whether we are capable of formulating such a question correctly at all. The words outside, near, and outside belong to the geometry of our space. If the universe itself includes all available space, then the familiar notion of the outer region may not make sense. The extra dimension does not necessarily lie somewhere beyond the distant border. It can pass through every point of the known world, remaining inaccessible to the movement of ordinary matter. In this case, the boundary between our reality and the broader structure does not run at the edge of space. It is present everywhere, but it is hidden by the properties of space itself.
This is one of the reasons why such ideas are difficult to depict. Any visualization is forced to use three-dimensional shapes, surfaces, membranes, spheres, and infinite dark spaces in between. But the real multidimensional structure, if it exists, may have nothing to do with these images. They only help to get closer to mathematical concepts that cannot be fully conveyed by the usual sight. When a brane is depicted as a thin sheet, it does not mean that our cosmos is literally a flat film. There are three spatial directions available to the beings within it, and each seems to be complete. The subtlety of the brane refers only to an additional direction that may not be available to all known particles. The same is true of bubble universes. They don't necessarily look like glowing spheres floating in the void. The word bubble describes an area where inflationary expansion has stopped and a certain vacuum state has emerged. Its internal geometry can be enormous or even infinite, despite the fact that in the mathematical model it originated as a local region.
From the inside of such a universe, it is impossible to see its external form. An observer would perceive space as a vast cosmos filled with galaxies, rather than the interior of a small bubble. This shows once again how much the appearance of the structure depends on the position of the observer and the measurements available to him. But could the collision of two bubble universes leave a mark? Theoretically, such an event could disrupt the homogeneity of the early cosmos. In the CMB, ring-shaped or disc-shaped regions with unusual temperature characteristics could be preserved. However, similar features can occur randomly or be the result of data processing. Therefore, one unusual spot is not enough to declare it the trail of another universe. For serious confirmation, a set of features that exactly match the prediction of a particular model would be required. They would have to be repeated in different observations and not explained by simpler processes. So far, there is no such evidence.
Similar caution is needed when discussing the unusual structures of the cosmic web. Huge walls of galaxies, Giant voids or unexpectedly large clusters are sometimes presented as possible violations of standard cosmology, but most such objects do not mean that the universe is part of the outer network. The cosmological principle states that on sufficiently large scales, the distribution of matter becomes approximately homogeneous and isotropic. This does not prohibit the existence of gigantic structures. The question is how often they should occur and whether their sizes are consistent with standard model statistics. Even if an object is found that is difficult to explain, it will not yet be direct evidence of multidimensional hyperstructure. First, you will have to check the accuracy of the distances, the boundaries of the object, the methods for isolating its components, and the probability of accidentally combining several independent regions into one proposed structure.
Science rarely moves from one anomaly to a new picture of reality. Usually, an unusual observation first forces you to refine data, revise patterns of structure formation, and check for systematic errors. It is only after the exclusion of simpler explanations that there is a reason to speak of a new physics. But it is anomalies that sometimes open the way to fundamental changes. A small discrepancy may be the first sign that an existing theory is incomplete. Therefore, the search for unusual signals continues, even when the probability of a sensational discovery is low. Gravitational waves of the early universe may be of particular importance. Unlike light, they are able to carry information about epochs when matter was still opaque to photons. If the primary gravitational background can be detected, its properties will help test different scenarios for the origin of the cosmos.
Inflation models can create a certain spectrum of gravitational waves. Episodic scenarios usually predict a different picture. Accurate measurement of such a signal could exclude entire groups of hypotheses, or conversely, increase interest in them. However, the primary background is extremely weak. It must be distinguished from gravitational waves that occur during the mergers of black holes, neutron stars, and other astrophysical processes. In addition, some of the possible signal is sought through the subtle polarization of the CMB, where the dust inside our galaxy creates a lot of interference. Even successful detection of primary waves will not necessarily prove the existence of brains. It will provide information about the energy scale and dynamics of the early universe, after which several models will compete for the best explanation of the data.
Perhaps the decisive clue lies not in the sky, but in the properties of black holes. They are the ones that unite strong gravity, quantum effects, and information, three areas between which deep contradictions remain. If matter falls beyond the event horizon, its quantum state should not disappear without a trace. But the classic description of a black hole preserves almost no information about what it was formed from. When you take into account the slow quantum radiation and the possible evaporation of a black hole, the question arises, where does the information go? If it is destroyed, one of the basic principles of quantum theory is violated. If it persists, it is necessary to understand how the information about the internal state is encoded in the radiation or on the event horizon.
It was the information paradox of black holes that became one of the main sources of ideas about the holographic nature of space. It shows that geometry, quantum information, and the boundaries of space can be connected much deeper than previously thought. Perhaps the event horizon is not an ordinary surface. It can store information about everything that has crossed it in an extremely complex quantum form. Then the inner volume of the black hole and the data at its boundary turn out to be two ways of describing the same system. If such duality exists not only for black holes but for entire regions of space, then the three-dimensional universe may indeed have an equivalent description at the boundary of a smaller dimension. But here an important difference arises. An equivalent description does not mean that one of them is real and the other is illusory. In physics, two mathematical pictures can be equally fundamental if they accurately convey the same processes.
Therefore, the statement that we live on a flat surface oversimplifies the holographic principle. We live in a world that is perceived and physically acts as a three-dimensional space. Even if there is a full description on the boundary, that doesn't make the depth false. it is much more accurate to say that the amount of independent information within a region can be limited by its surface. The spatial volume then contains not so many fundamental degrees of freedom as ordinary geometric intuition suggests. On a huge scale, this is almost imperceptible, but at extremely small distances, such a principle may mean that space cannot be divided indefinitely. If there were an unlimited number of independent states in each infinitesimal volume, the information capacity of the region could exceed the limit associated with the formation of a black hole.
This leads to the assumption of a minimal scale, at which the usual concept of distance loses its meaning. Below it, space may not be smooth, but quantum, discrete, or even arising from relations that do not have a geometric shape. We do not know which of these pictures is correct. There is no direct representation of the quantum structure of space. It is impossible to view it through a microscope because the estimated scale is so small that the required energy itself could radically alter the area under study. Trying to study extremely short distances requires extremely short wavelengths and high energy. But concentrating too much energy in a small volume can lead to severe curvature of space or even the formation of a microscopic black hole. This creates a fundamental restriction on direct research on the smallest scales. Therefore, the deep structure of space has to be restored indirectly through mathematical coherence, the properties of black holes, cosmological observations, and rare effects that can persist at available energies. Perhaps there is no single picture that looks like a familiar object at all. At a fundamental level, reality can admit of several equal descriptions. In one, the space is three-dimensional. In another, the same system is represented by quantum states at the boundary. In the third, geometry arises from a network of connections. Then the question, what does everything really look like, can be posed incorrectly. Appearance refers to objects within space, whereas a fundamental theory must describe the origin of space itself.
This is like trying to determine the form of a law of nature. The law is not required to have a type, color, or position. It expresses the relations between quantities. Similarly, the deeper level of reality can exist not as a hidden room behind the universe, but as a system of relationships from which dimensions, distances, and motion arise. If this idea is correct, the cosmic canvas takes on a new meaning. This is usually the name given to a network of galaxies and dark matter that stretches across the observable cosmos. But on a deeper level, space itself can be a canvas woven of quantum bonds. Galaxies are then not located on an empty, unchanging background. They exist within a structure that itself is capable of stretching, bending, oscillating, and possibly forming from information.
The expansion of the universe already shows that distances are not stationary. Galaxies can move away from each other not only because they are moving through space, but also because the scale of the space between them itself increases. At sufficiently large distances, the speed of increasing the gap can exceed the speed of light without violating the limitations of relativity. No object moves locally through space faster than light. The geometric distance between distant regions itself increases. This leads to the existence of cosmological horizons. Some of the galaxies whose light we see today may already be in areas from which the signal emitted now will never reach us. The space between us is expanding so fast that new photons won't be able to travel the growing distance. Over time, the distant universe will become less and less accessible. If the accelerated expansion continues, more galaxies will disappear below the horizon. They will not cease to exist, but their future light will no longer be able to enter our area.
Thus, even within the same universe, regions arise that are forever causally separated from each other. These are not separate universes in the full sense, but for future observers, they will become inaccessible worlds with which it is impossible to exchange a signal. And if the cosmos is already capable of separating its own regions by insurmountable horizons, the existence of a broader structure becomes even more difficult to verify. Anything beyond the causal boundary can affect the mathematical picture, but leave no accessible messages. However,
Our observable horizon is not a fixed wall. It is related to the age of the universe, the history of expansion, and the movement of light. We see increasingly ancient regions, not because we are approaching the physical edge, but because we receive radiation that has traveled to us for almost all of cosmic history. Behind every distant galaxy lies not an outer boundary, but an even earlier epoch. The deeper the gaze is directed, the closer the observation comes to a time when galaxies did not yet exist, and matter was in a hot and dense state.
But even the relic radiation does not show the beginning. It forms the surface of the last scattering, the limit beyond which the early plasma was opaque to light. Everything that happened before cannot be seen directly with conventional telescopes. Therefore, the origin of space remains hidden not only by distance, but also by the physical state of early matter. To penetrate further, you need other carriers of information, gravitational waves, neutrinos, or indirect traces in the distribution of matter. Perhaps it was there, beyond light transparency, that there were signs of whether the Hut universe was a beginning, a transition after compression, or the result of a process in a larger, multi-dimensional structure. So far, this question is open, and the closer physics gets to it, the clearer it becomes. The mystery is not just what is far away, it lies in the very reason for the existence of distance.